Good morning. Today we will see some key points for the compression members. So now, which is unit number 2. So we have first, what is compressive strength? Design compressive strength. So we have this. So you can see over here. So we have design compressive strength, PD of a member, and that is equal to AE into FCD. So we have from this, we are going to get compressive strength of the members. Now we have two terms, AE and FCD. AE we have effective sectional area as defined in 7.3.2, and FCD we have according to 7.1.2.1. So these two criteria are important to find value of AE and FCD. Means to get PD, we require only these two values. Now we will see how we will go with these two values. First we will go with AE. Now effective area AE. So we have 7.3.2 effective sectional area. So except as modified in 3.7.2 class 4. The see except means except class 4, the gross sectional area. So here you can see the gross sectional area shall be taken as the effective area. Means we have to take effective area that is equal to gross cross sectional area except class 4. Means we have 4 class. So for class 1, for class 2, and for class 3. For all these three classes, we have to use AE equal to AG. So you can see over here welding, bolting and riveting so long as this section is semi-compact or better. So now you can see we have class 1 which is plastic. So here for this class we have AE equal to AG. Then you can go with class 2 compact. Here also I can use AE equal to AG. And then third class 3 semi-compact. Then here also I can use AE equal to AG. Better semi-compact or better means we have class 3, class 2, class 1. These classes we have class 1 and class 2 we have better than semi-compact, that is class 2. So class 4 we are not going to consider, or here my AE is not equal to AG. In this case, my value of AG, that is not equal to AE. So here my value that is less than AE. We have to find in this case that is effective area. So we will not go for this. How we will find effective area? Because we are going to consider only three sections. Class 1 plastic, class 2 compact and class 3 semi-compact. So first it is fixed that my value of AE is always equal to AG. Now important, we have to check this class. How we will see go for the classes? So we have table 2 where we are going to get classification of section. Now here this is for angle section. So axial compression, it may be single angle, double angle with the component separated, and all these three criteria should be satisfied. Now what is B, what is D? So we have B is one leg and D is other leg. So we have this will be B. And then we have D, and then we have this will be my thickness. So this is T. And by using these dimensions, we have to check that my class is semi-compact or not, because in this we do not have these classes. So we have only two classes, semi-compact or class 4 we have slender, but we are not going to consider slender sections. In the second we have, this is for eye section, channel section, box section, and here we have two. One we have that is for outstanding element of compression flange, means this is for flange, rolled section and welded section. And then we have for web, that is for eye section, we can find from this. And for web of channel, we have these 42 values. So we have to use these values, and by using these values given in table 2, we have to decide the class of the section, and by this class we are going to get value of AE equal to AG. Never provide slender section, because slender section is not economical section, and therefore avoid slender section. Then we have second part, that is design compressive stress. Now to find design compressive strength, we require three values. First value we require, that is L effective. Second value we require, that is minimum radius of gyration. And third value we require, that is lambda, which is L effective upon R minimum. So we require these three values to find value of FCD, that is design compressive stress. Now this design compressive stress we require for two types, or we are going to divide sections into two types. One that is single angle section, and second we have all other section than single angle section. And in that single angle also, again we are more specific with, it is loaded through one leg only. It is loaded through one leg only. Only that we are going to consider while we are going to determine, that is design compressive stress. Now it is very clearly mentioned over here, the flexural torsional buckling strength of single angle loaded in compression through one of its leg. And generally we are going to load single angle with one leg only, and therefore we have to find lambda E. Now we can see how we will go with this. Single angle stress 7.5.1, and this is 7.5.1.2. 1.1 is concentric loading. If it is concentric loading, then we have to go 7.1.2. But for single angle, it is not possible to go by concentric loading. So in single angle, we are loaded with one leg, and therefore we have to use 7.5.1.2, which is detailed below. In this, we have given this formula, first lambda VV, L upon RVV upon epsilon pi square E upon 250. Now we can find epsilon, we can find pi square E we know, and we can find these values. Now RVV, because we have four values of radius of gyration, and for single angle section, your value of RVV is minimum. So from this I will get value of lambda VV. Then we have lambda phi. We have this value of lambda phi, we can find by using this B1 plus B2, and we have B1 equal to one leg, which is D, and B2 we have another leg which is equal to B, and by using this leg I will get value of lambda phi. Knowing these two values, I have to find lambda E, which is effective slenderness ratio. And for this, I require value of K1, K2 and K3, because now I know lambda VV, I know lambda phi. So K1, K2, K3 we have to find from table 12. Table 12 we have given, which depends upon your number of bolts. So if number of bolts are greater than equal to 2, then we have to see which connection we have to use. And if number of bolts is equal to 2, then again we have to decide the connection. If connection is given, then we have to consider value accordingly. If not given, then we have to assume the connection, and by assuming connection, we have to take value of K1, K2, K3. So by substituting value of K1, K2, K3, we are going to get value of lambda E. And knowing value of lambda E, we can find phi. In phi, so this value we have lambda E. This is also lambda E. And from this we will get phi. Now unknown we have here alpha, and alpha depends upon your the table 7, and that alpha depends on your buckling class. How we will find buckling class? So buckling class we are going to find by using table 10. Table 10. And now for single angle section, my buckling class is always C, that is 0.49. So I have to take 0.49 while I am going to use, that is single angle section. Knowing phi, I can find value of FCD, and knowing FCD, we can find PD, because already we have seen the formula for PD, which is equal to AE into FCD. So effective slenderness, this is most important, but for single angle, we cannot use tables given in IS code, which are 8 ABCD, that is for reduction factor, and 9 ABCD will gives you direct design compressive stress. So this part we have, that is for single angle strut. Now we will go all other sections. In all other sections means which sections we have? We can have this double angle section, double angle, then we have any other section, that we have channel, we have beam, we have built up section. So all other sections comes under this part, built up sections. So all these other parts are over here. So now we will go procedure for this to calculate compressive stress. Now in this we have to first calculate effective length, L effective. Now L effective we have to use 7.2.4, and there that is given for compression member in trusses, that value ranges between 0.7 to 1. So 0.7 generally we are taking for welded connection, and 0.85 we are taking it as for bolted connection. So for these two we are going to use that is compression members in trusses. Now for this, we require minimum radius of gyration. So to find design compressive stress, we require two values. One value is L effective, because lambda slenderness ratio is L effective upon R minimum. Now L effective we will get from 7.2.4, and now we are interested with R minimum. R minimum depends upon your section to calculate slenderness ratio. Now we will go one by one. We have double angle connected on opposite side of gusset plate. I already mentioned this, 0.85 for bolted and for welded 0.7. Now we have on opposite side of gusset plate, and then we have ZZ section, YY section. Then what will be minimum? So now if your angle is equal angle, whatever now we are saying for equal angle. Equal angle. And now in this, my value of YY will be somewhere here. YY individual. Huh? So this is Y individual. We have here Y individual. And this is Y whole. And Z I also here and Z whole also here. So whatever Z we have, so we have same for individual also and for whole also, and therefore we have to find RYY. How we will find RYY whole? So that is equal to root of RYY individual square plus H square. What is H? H is the distance between the individual axis and whole axis. So distance between this will use you H. And how we will get this value of H? This will be CYY plus thickness of gusset plate by 2. And from this we will get value of H. And therefore, this value definitely in equal angle section, we have RYY equal to RZZ. And therefore, RYY whole section will be always greater than RZZ. And therefore, we will take R minimum equal to RZZ in case of equal angle. If it is unequal angle, you have to find RYY whole, and then you have to check RZZ and RYY whole. Minimum of 2 we have to consider, minimum of 2. But if equal angle section, then directly we can take R minimum equal to RZZ. And then we can find lambda L effective upon R minimum. So next, angles connected on same side of gusset plate. Now you can see we have on same side of gusset plate. Here we have again two positions. This is first position where we have these axes. Now you can see we have this will be y axis. Now in this case my y individual and my whole y whole section are same. Now z individual we have over here. So we have z individual and z individual, and then we have to find z whole. So this will be z whole. And now in this case, again I am mentioning for equal angle section, we have y individual equal to yw, and equal section we have that is rzz, and that is equal to ryy, and therefore we have ryy as it is, because rzz whole section again you have to calculate by using same formula, rzz individual square plus h square. And again we have in this case now we have only this value which we will say it as cxx. No thickness of gusset plate we have to consider over here, and therefore we can write over here rzz individual square plus cxx square. And then we have to see minimum is ryy and rzz whole section. Minimum of 2 we have to consider as r minimum if we have unequal. If we have equal, then directly we can take r minimum equal to ryy. Then we have in this also, and in this case we have rzz is minimum, because ryy again we have to find out. My individual axis is again ryy we have over here and we have over here, and then we have to find this value. Now we have the angles in star, and then in case of angle in star, so we can have these as star sections. And then in this case we have ZZYY. So now we have Z individual we have over here, Z whole individual over here. So Z individual, we have Z whole. Similarly, we have Y individual, and then we have Y whole. So in this case, star angles, we have to find Y whole. So RZZ, and we have to find RYY. So we have both these values that are going to be same if we have equal, and then if we have unequal, then we have to again find the values. Now again we have two axes. You can see over here. So we have RUU axis. When we have star angles, we have to consider again this third axis, which is RUU, and fourth axis we have to consider RVV. So we have this VV axis we have to transfer over here, and this is my value of H. And this H value for RVV, we are again going to consider it as CXX plus thickness of gusset plate by 2 whole square. For RVV also, exactly need not required to calculate, we can consider this and we can find RVV. Then we can find RUU, and minimum of all these RZZ, RYY, RUU and RVV we are going to get as R minimum, and knowing R minimum we can find lambda value, and for this star angle section. So now we can go, channels are placed back to back, so you can have like this. So now as we are going to provide, how we will provide S? So S value should be provided in such a fashion, my RYY is greater than RZZ, and automatically if we are going to provide a RYY in S in such a fashion, then my R minimum is always RZZ, and then directly I will get this value, that is RYY whole equal to RZZ, and that is in this way, and RYY is definitely greater than RZZ is less than RYY whole. Now you may say, sir, you are equating these two values. So equating means whatever S value we are going to get, S required, we are going to get from above, we will provide S greater than S required, and if you will provide S greater than X required, automatically your RYY whole greater R RZZ, and therefore to find value of lambda, I can directly go with RZZ. So lambda equal to L effective upon RZZ. L effective in case of these columns, we have to use table 11 given in IS 800. Then we have next channels placed toe to toe. So the difference we have in this case, so just you can see CYY we have from this side, and we have this value B minus CY. See, in last also I will just show you how we are going to consider this value of H. So value of H we have center of this will be y whole. So my value, this value will be S by 2, and this is Cy. So the distance between individual axis and whole axis is Cyy plus S by 2, and this becomes my value of H. And therefore we have this formula Cyy plus S by 2 whole square, which is H. Now in this case, what will happen? So I have just mentioned this B minus Cyy, and what your whole section is again is at center, and then we are going to get this value, that is H. Here H becomes B minus Cyy plus S by 2, and then we have this will be portion in this fashion, and then we can have L effective upon R minimum. Again S you have to provide, that is greater than S required, as S provided greater than S required, and therefore RYY whole greater than RZZ, and therefore we can take directly L effective upon RZZ. Now, once we know value of this, then we have to go for the tables. Then how we will decide the table to determine design compressive stress? We have given 4 tables, 9A, 9B, 9C, 9D. These 4 tables are given which will decide your compressive stress, and this depends on your buckling class, which is given in table 10. For I section, we have 2 criterias. One, that is H by BF greater than 1.2, and then 2 thickness criterias. Lower we have to always consider it may be B or it may be C. If T H by BF is less than 1.2, it is C or it is D. So then we can have this second channel angle T and solid section. So we have this any single section, if we will consider section, your buckling class is C, and any built up section we have buckling class C. And from this we are going to decide the table A, B or A, B, C or D we have to use. And then knowing this, for A we have table 9A, then B, 9B, 9C, 9D. Now we know value of lambda, that is slenderness, which we have calculated L effective upon R minimum. In this table you have given lambda value, then you have given Fy value on this side, and then you have value of FCD in these. So Fy, if bolt in one question paper, bolt is given of 4.6. If bolt class is given, then your value of Fy is 10 into 4 into 6, which is 240. You have to take 240, and then for that column, you have to consider FCD. If not given, then in most of the cases, we are going to use 250 Newton per mm square. How we will find this? So if you have class 5.5, then we have 10 into multiply these two values. So that will be 250. So if you have 8.8, then you have 10 into 8 into 8. So it will be 640. So likewise, you will get value of Fy. And knowing value of FCD, we can find design compressive stress. So by using the formula which already we have seen, and that formula we have PD equal to AE into FCD. So this is for analysis. And in case of design, you have to go only for two cases, two steps. One AG are required, axial compressive load, allowable compressive stress, and then you select the section. And after selecting the section, you have to follow these steps. So this is at a glance for your compression member. Now we will stop here only. Thank you.